The title of my talk is A Machine Proof of an Inequality for the Sum of Distances between 4 points on the unit hemisphere using Maple software. This is a joint work with Yaochen Xu, Jianlu, and Liang Yuchen. So, the outline of my talk. First, introduction to the problem. Second, mathematical methods. Third, Maple solution. Includes local analysis, global search, and 4, Maple programs, and finally, open problems for further study. First, introduction to the problem. If we cut the unit sphere into 2 hemispheres and we put 4 points on the hemisphere, we want to find the maximum of the sum of the mutual distance between these 4 points. There are 2 possible solutions according to the symmetric analysis. First plan, we put 3 points on the equator to form a regular triangle, and we put the 4th point D on the North Pole. The second plan is we put all 4 points on the equator to form a regular square. We will find in first plan the sum is about 9.43, and in the second plan the sum is about 9.65. So the second plan is slightly better. We also use the Maple to search the other possible optimal configurations. We use the Monte Carlo test. Also, we used the global search. We didn't find any better solutions. So we will prove the main result as follows. For any 4 points A, B, C, D on the hemisphere of radius 1, the sum of their mutual distance is not greater than 4 plus 4 times of square root of 2. And up to congruent, the optimal configuration is formed by these 4 points printed in red. Now, the mathematical methods. It includes 3 parts. In part 1, we use human analysis to prove that if several points on the hemisphere satisfy that the sum of the distance is maximum, then 3 of them must be on the equator. We will also prove some other minor results for reducing computation in part 3. Part 2, we will use Maple software to do some symbolic computation for proving that the empirical optimal configuration is indeed a local optimal solution. This is easier, and we will also determine the size of the neighborhood of the local maximum. This part is relatively complicated. And the part 3, Maple numerical computation. In that part, we will prove that on the other region, there is no better solution. We will use global search with Maple exact numerical computation. So here is lemma 1 proved by human analysis, which says if A, B, C, and D are 4 points on the upper hemisphere, so that the sum of the distance is maximum, then the center O of the sphere must be contained in the interior of the polyhedron ABCD, or O lies on one surface of ABCD. In the right, we show the 2D analog of above property. Now, lemma 2 proved by human analysis. We suppose ABCD is one optimal configuration, and D1, D2, and D6 is a permutation of the 6 distances from smaller to larger. Then we have these 6 estimations of the distances. This lemma has a corollary 1. If ABCD is one optimal configuration and A, B, C are on the equator of the hemisphere, and D is the 4th point, then the distances between D and the North Pole N is larger than 0.8044. Here, lemma 3. Assume that ABC are 3 points on the equator, and D is a 4th point on the hemisphere, such that the sum of the distances is maximum. Then we will have some inequalities of AC, BC, and AB. Also, the coordinates of point D, as shown in the expression numbered 1 and 2. Here, we start the part 3. So, the first part is maple solution for the local analysis. We will prove that if A, B, C, D are these 4 points, then they forms a critical point of the distance sum function. And secondly, we will prove that this is indeed a local maximum point according to some analysis to Hessian matrix. Third, we can construct 3 neighborhoods of BCD as shown in expression 345, so that if ABC and D lies in the Cartesian product of A and UVW, then this point is the unique local maximum. So this is proved. First, we apply lemma 4 to transform the sum of 6 square roots to some fractionals, and we show that the fractionals, the denominator is a positive definite polynomial, and the nominator numerator, which is h2 plus h3 plus h24, the sum is also the sum is a negative semi-definite. So here we show more information of the Q and H2, H3, H4, and up to H23, H24, like this. We will use this lemma to change a monomial to the sum to some quadratical polynomials. Then we will prove the upper bound of H3, H4, and the sum of H5 plus H6 plus H24. Therefore, the sum of H2, H3 up to H24 is not greater than a negative semi-definite polynomial. So this completes the process of the local analysis. Namely, we have constructed an isolated region formed by the Cartesian product of point A and the neighborhood UVW. In that region, the point ABCD is the unique local optimal point. So the second part for the maple solution is global search. So we will prove that if we take M as a Cartesian product of S1, and S2, and we take the U0 as shown in the configuration of right hand as a Cartesian product of UVW, then in the set M, set minus UVW, we will show we can divide this part into large amount of small pieces of appropriate size, so that in each small piece of the subdivision, the inequality FA of BCD is not larger than 4 plus 4 times square root of 2, valid by estimation. So first, we reduce the sum of distance fraction to a fraction of 6 variables, and this is done by projected to the fourth point D, which is x3, y3, z3. We project this point to the unit disk in the equator plane. Therefore, the sum of distances will be a fraction of 6 variables, which formed by a sum of 6 square roots. Now, we partition the state space of variable. In the initial, we cut the unit disk into 246 small squares. We will see that the unit disk is covered by 200 24 small squares, and the unit circle S1 is covered by 60 small squares, which contains the orange-colored 30 orange-colored small squares and 30 green-colored small squares. So then the state space of variables contains 20,160 the combinations of small squares. And the length of the small square is 1/8 now. Now we reduce the state space of variable by applying the lemma 2 and 3 to remove non-optimal combinations. So we proved that point A must be contained in the 11 small square in orange color, and point C should be contained in the 11 small square of green color, and point D must be contained in the 88 small squares, which is recorded in the right side of this slide. Now, we estimate the sum of distances, therefore we can remove more non-optimal combinations. So here we give one example of this. After this test, we got 6,348 combinations excluded, and the remaining combinations needed for further processing is 4,300. Now, the second round of global search, we use divide and conquer method. So here, we cut the small square SB, SC, SD, each to 16 small squares, and we check their intersections with the equator and the unit disk. Then we got subdivisions of around 300 new combinations. In each new combinations, the square root, the square is of h 1/32. Now, apply lemma 2 and 3 to test the individual distance and the sum of the 6 distances. We found that among 1,105,782 combinations, there are only 19,206 combinations need to be investigated further. So in the third round, we will do depth-first search. Now we have 19,206 three-square combinations as shown in the yellow picture. The length of the squares is 1/32. We cut this combination into around 300 newly three-square combinations where the square edge is 1 over 128. In the breadth first search, we would process all smaller combinations before the next step, as shown like this. But in the depth first search, if we checked the first combination and it passed the test, then we go to check the second combination. Assume that the second combination has not passed the test. Then we divide this combination into 2 to 300 new combinations, in which the length of the small squares is 1 over 512. Now, if all newly constructed 3-square combinations passed the test, then we go back to process the combination 003. Otherwise, we do partition further. So compare with the breadth first search. Depth first search can save memory space. So if we cut 19,000 combinations of 3 squares of age 1 over 32 into small pieces, we would use at most 78 million units to save the newly created object. Apply the depth first search. We found that among the 19,206 combinations, 19,007 combinations had passed the upbound test when they were divided into squares of age 1 over 128, which means just one step of subdivision. And the rest, 199 combinations, had passed the test when they were divided into squares of age 1 over 512, which means 2 steps of subdivision. So this completes the computation of the global search. So it shows that outside of the constructed neighborhood, U times V times W, the sum of the distance is also less than 4 plus 4 times square root of 2. Now we have some statistics about maple computation time. In the first round, we used only 16 seconds. In the second round, we used 1,170 seconds. And in the third round, we used 8,777 seconds. So the time for the symbolic computation for the local critical analysis is not included because they are relatively very fast. Now we recall the local maximum neighborhood again. So this is a summary of the inequality. So in the local analysis, we proved that if A, B, C, D are in the small neighborhood, we have the inequality. In the global search, we proved that if BCD is not in the Cartesian product of UVW, then we also have the inequality. So combine these two results, we proved the main result of our talk. So now we show some message of maple program. The maple program of the local analysis can be provided by email. We also attached as a maple file in the conference materials. And for more detailed description of the local analysis, a paper can be found from the Proceedings of the ADG 2021. For the maple program for the global search, we submitted to as the easy chair preprints numbered 6349. We also attached as a material conference. So finally, we show some open problems for further study. Namely, we put 5, 6, up to 12 points on the hemisphere. We want to find the maximum of the distance sum between these endpoints. Then the empirical computation shows that for n equals to 5, the result is 5 points on the equator. And for all other cases, we put 1 point on the North Pole and the other points on the equator. So this is all the talk of this maple conference this year. We wish a great success of maple conference this year, and thank you for your attention. And I wish very much next year, the maple conference, we will see some real maple in Canada. Thank you again.